Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Maxwell-Boltzmann distribution law, or we can say it as Maxwell-Boltzmann energy distribution law. Let's begin. Let we consider n number of molecules, n be the number of molecules are enclosed in an isolated vessel of volume V. Volume V means we take an isolated, this one is the isolated vessel and its volume is V, and there are a number of molecules. N is the number of molecules within that of isolated vessel. These molecules are in random motions. These molecules motion like this, that direction, means random motions within different velocities. Different molecules possess different velocities, so they random motion with different velocities, hence they possesses different momentum and energies. Different molecules have different velocities and also different momentum and energies. During their random motions, what happened? The molecules are colliding with one another, they collide one another and with the walls of the vessel. They collide one another and with the walls of the vessel. Therefore, their momentum and energies are continuously changing. Due to the collision, their momentum and energies are continuously changing. Why? Since the gas is thermally isolated, we say that is the isolated vessels. Since the gas is thermally isolated, therefore we can say the total energy U remains constant here. So the total energy U of that of isolated system treated as constant. Now, in this case, the gas remains in equilibrium state. Gas, we can say that is the equilibrium state or most probable macro state. Gas has equilibrium state or we can say that is the most probable macro state. Equilibrium state or most probable macro state. Equilibrium state or most probable macro state. And what should be the energy distribution of these n molecules in that of most probable macro state? Since these gas molecules are equilibrium state or most probable macro state and the total energy of that of system U is constant, then how the energies are distributed? The energies are distributed among a number of molecules that are enclosed in that of isolated vessel. So we have to calculate how that energy is distributed. Let here we take the ideal gas. These are the ideal gas. Ideal gas. Let total energy of that of ideal gas, the total energy, let the total energy of the ideal gas is divided into total energy, that is U, total energy U of the ideal gas is divided into K intervals. K intervals. U amount of energy is divided into K number of intervals. This is similar as N molecules be distributed in K components. That is very similar. This is similar as N number of molecules, N molecules are to be distributed in K compartments. Let you take here is the K intervals. K intervals means this is 1 interval, 2 interval, 3 interval, 4 interval, 5 interval, 6 interval, like that of. Let you take K number of intervals, 1, 2, 3 up to K number of intervals. That indicates that N molecules are to be distributed in that of K compartments. Here is the number of compartments, 1 compartment, 2 compartment, 3 compartment, like K number of compartments. So N number of molecules are distributed in that of K number of compartments. Let you say U1, U2, U3, UK are the mean energies of these intervals. This is the first interval, let that energy will be U1. This is the first interval energy. This is the second interval, let the energy will be U2. This is the third interval, let the energy will be U3, like that of. For kth interval, this is the kth interval, let the energy will be UK. So write let U1, U2, U3 up to UK are the mean energies, of intervals like 1, 2, 3 to K respectively. And here the number of molecules, let N1 be that of first component, N2 be that of second component, like that of Nk be the number of molecules in that of respective components. So here we write let N1, N2, N3 up to Nk are the number of molecules of intervals 1, 2, 3 up to K respectively. That component have mean energy U1 and number of molecules N1, like another compartments. Now let the components are further divided into large number of elementary cell. These components, let I take that is a component, this is a component. That component further divided large number of elementary cells. This is the compartment, compartment or interval, and each interval is divided into, this is a large number of elementary cell. These are known as, this is a elementary cell, elementary cells, each of equal size. So here write each compartment, let those compartments are further divided into large number of elementary cells, each of equal size, This is a compartment. That compartment is divided into large number of elementary cells. Each cells have equal size. Again, let you say these compartments are named like, let G1, G2, G3 up to Gk are the number of elementary cells, of the compartments, like 1, 2, 3 up to k respectively. Understand that point, what it say. This is an interval. That interval, that is interval number 1, it has the mean energy U1, a number of particles in that of compartments will be N1, and that compartment is further divided into large number of elementary cells having equal size each of that of elementary cell, and these compartment, the number of elementary cells will be G1. That compartment, the number of elementary cells will be G2. That compartment, the number of elementary cells will be G3. Like that of last compartment, k number of compartments, the number of elementary cells will be Gk. Here the number of particles be N1, here the number of particles be N2, here the number of particles N3. Like that of k number of compartment, the number of particles will be Nk. Okay, that is a compartment. That compartment has mean energy U1, number of particles N1, and further that compartment is divided into elementary cells, and here the number of elementary cells will be G1. In compartment 2, the number of elementary cells will be G2. Like that of k number of compartments, the number of elementary cells will be Gk. Okay, these are some basics. Now the problem is like distribution of n molecules into k compartments of unequal size, which are further divided into large number of elementary cells, each of equal size, as we discussed here, each of equal size here. Now let Ni are the number of molecules, and Gi are the number of cells, of ith interval or ith compartments, or interval. Look at that. These are the intervals 1, 2 up to k. Here let I take, this is, let I take, that is the ith interval. This is the ith compartment. Ith compartment. What happened here? In that of case, let the Ni be the number of molecules in that of ith component, and it has the elementary cell be Gi be the elementary cells of that of ith compartment. Now, what should be the most probable thermodynamic probability of that of macrostate? Let we know that the thermodynamic probability of most probable macrostate of what? Most probable macrostate of n1, n2, n3 up to nk are given by, we write it mathematically, the most thermodynamic probability of most probable macrostate, that is the thermodynamic probability W of most probable macrostate of n1, n2, n3 up to nk are given as, that is the most probable macrostate will be given as n factorial summation over I from 1 to k Gi to the power Ni divided by Ni factorial. This is the thermodynamic probability of most probable macrostate having the macrostates n1, n2, n3 up to nk. Taking the logarithm both sides, what happened here? Taking the logarithm both sides, that is ln w ln w is equal to ln a into b, that is ln a plus ln b, that will be ln n factorial. This is the n factorial, this is n I factorial, this is n with the total number of molecules, that is ln n factorial plus summation over I from 1 to k here we take ln a by b, that is ln a minus ln b, and ln a to the power m something, that is m to that upside. So it will be Ni ln Gi minus summation over I from 1 to k ln Ni factorial. First ln ab, that is ln a plus ln b, then ln a by b, that is ln a minus ln b, and ln then a to the power m, that is m ln a. These are the some basics of logarithm concept. Here assuming that n and ni are very large numbers, hence we use Stelling's approximation, Stelling's equation as What is that of Stirling's equation? If we calculate ln n factorial, then it will be n ln n minus n. This is the Stirling's approximation. Here we use Stirling's approximation in that of given equation. So here we use Stirling's approximation and expanding it. So ln w, therefore ln w is equal to n ln n minus n. Here we use the Stirling's approximation plus summation over I from 1 to k ni ln gi minus summation over I from 1 to k. Here also use Stirling's approximation, that is ni ln ni minus ni. Okay, now we solve that equation. Is equal to n ln n minus n plus summation over I from 1 to k ni ln gi minus expanding these two brackets summation over I from 1 to k ni ln ni minus minus plus summation over I from 1 to k ni. Look at that equation, that is summation over I from 1 to k ni, that is the total number of molecules n, that is the total number of molecules n. So we write here, that is n ln n minus n plus summation from I from 1 to k ni ln gi minus summation over I from 1 to k ni ln ni, here plus that value will be n. So plus n minus n cancel out, the only term exists, that is ln w is equal to n ln n plus summation over I from 1 to k ni ln gi minus summation over I from 1 to k ni ln ni. Since here ni and gi are constants, so we take the differentiation. Since ni and gi are constants, now differentiating that equation, we have differentiating both sides, we get ni and gi are constants, another terms are varies. So d ln w is equal to, that term will be 0, that term treated as constant, not ni, that is n, not ni is variable, only n and gi are constants. So here the term is constant, it will be 0 plus its differentiation, ni is variable, gi also variable, sorry gi constant, so ni is variable, therefore that is summation over I from 1 to k dni ln gi, that term is constant, that is the only variable term, minus these two terms are vary, so we use the differentiation rule here, that is summation over I from 1 to k dni ln ni, differentiation of first term, second term treated as constant, minus differentiation of second term, first term treated constant, so summation from I to k, that is ni. Next its differentiation ln ni, that is 1 by ni dni. Okay, is equal to summation over I from 1 to k dni ln gi minus summation from I to k dni into ln ni minus ni cancel out, only dni I from 1 to k, that is dni. That value dni, the summation from dni, change in ni will be 0, that term will be 0. Therefore we have summation 1 to k dni ln gi minus summation from I 1 to k dni ln ni. Therefore d ln w is equal to summation from I is equal to 1 to k, that is ln gi minus ln ni of dni. For most probable macro state, what will happen? For most probable macro state, the thermodynamic probability term, the thermodynamic probability is maximum. Thermodynamic probability is maximum, Therefore W thermodynamic probability be the W max, hence that a differentiation term d ln w term will be 0, since thermodynamic probability is maximum. Now applying the conditions, here we apply the conditions, as total number of molecules and the total energy of that of systems both are constants. Applying the conditions that total number of molecules n and total energy U of the system are constant. That is total number of molecules n, that is summation from I from 1 to k ni is constant, total number of the molecules in that of system constant, and total energy of that of system constant. So dn is equal to summation from I from 1 to k dni term is 0, and or that is right here, summation from I 1 to k dni is equal to 0, and total energy term 0, U be the total energy, that is summation of I from 1 to k ui ni, ui is the energy of ith compartment, ni, that term is constant. So its differentiation du is equal to summation over I from 1 to k, that is ui dni is equal to 0, or summation from I is equal to 1 to k ui dni is equal to 0, that is dni is equal to 0 and ui dni is equal to 0. These equations and that equation d ln w is equal to 0. We can combine these three equations as we write as equation 1, equation II and equation III. Now multiplying alpha here, multiplying alpha in equation 2 and beta in equation 3 and subtract these two equations from that equation 1, there will be no such result, the result will be 0 also, since these three are 0. So we combiningly write these three equations as multiplying a constant, so we write multiplying alpha by equation 2, equation II and beta by equation III and subtract from equation 1. So what we have now, multiplying alpha here and multiplying beta here and subtracting these two from equation number 1. So we have multiplying alpha to 2. So finally we get ln w minus summation over I from 1 to k, multiplying alpha here, so alpha dni minus next multiplying beta here, so I from 1 to k beta ui dni is equal to 0, or putting the value of ln w, the summation of I from 1 to k ln gi minus ln ni of dni, that is summation over I from 1 to k ln gi minus ln ni dni minus summation over I from 1 to k alpha dni minus summation from I from 1 to k beta ui dni is equal to 0, or taking all the summation I from 1 to k, in that bracket term it will be ln gi minus ln ni minus alpha minus beta ui dni is equal to 0. Look at that equation, as dni are independent variables, therefore the equation is valid only if the inside term when equal to 0. So we write here as dni are independent variable, so that equation will be valid only if the quantity inside the bracket will be 0. The quantity inside the bracket is 0. So inside that bracket term, that is ln gi minus ln ni minus alpha minus beta ui is equal to 0, or that is ln a minus ln b, ln a by b gi by ni minus alpha minus beta ui is equal to 0, or ln gi by ni is equal to alpha plus beta ui, or gi by ni is equal to e to the power alpha plus beta ui, or ni is equal to that term is gi by ni, gi by ni will be to the power something. So ni by gi, that is 1 divided by e to the power alpha plus beta ui, or ni is equal to gi divided by e to the power alpha plus beta ui. ni is equal to gi divided by e to the power alpha plus beta ui. That equation, this is known as Maxwell-Boltzmann law of energy distribution, law of energy distribution, or we can say that the Maxwell-Boltzmann distribution law, Maxwell-Boltzmann distribution law. And here ni by gi, here the term ni by gi is called that is the occupation index, that indicates, means occupation index means what is the number of molecules per phase space cell. That is the occupation index means that is the number of molecules per phase space cell, the number of molecules per phase space cell is known as the occupation index, that is ni by gi. In Maxwell-Boltzmann distribution, the value of ni by gi in this case ni by gi is greater than 1, very less than 1. The occupation index in case of Maxwell-Boltzmann distribution law is very less than 1. So in this way, with the help of this video lecture, we understand what is Maxwell-Boltzmann distribution law. Maxwell-Boltzmann distribution law we take the mathematical way to calculate. These are the mathematical way for most probable macrostate condition in case of thermodynamic probability. The relation is applied, and finally combining these equations we derive the Maxwell-Boltzmann distribution law, that is ni is equal to gi divided by e to the power alpha plus beta ui, which is known as Maxwell-Boltzmann law of energy distribution or Maxwell-Boltzmann distribution law. In this ni by gi called the occupation index in the sense that is the number of molecules per phase space cell. And in that of case, in case of Maxwell-Boltzmann distribution law, ni by gi, that is the occupation index, is very less than 1. So with this useful and informative notes, let me wind up this session. Thank you.